Have you ever looked up at a massive steel suspension bridge and wondered, how do engineers actually know those cables won't just snap under heavy traffic? Well, I'll tell you a secret. They don't guess. They know exactly how much steel can stretch before breaking, and they figure it out using the exact same physics you test right on a lab bench. Today, we're going to bridge the gap between a simple wire and towering skyscrapers. Welcome to today's Explainer. We're going to be mastering a classic Class 11th physics practical, determining the Young's modulus of a wire using Searle's apparatus. We'll be breaking down the physical steps, the forensic math, and a few hidden traps so you can execute this flawlessly and, of course, absolutely ace your Viva exam. Here is our roadmap for today. 1. Why materials don't break. 2. Hooke's law and elasticity. 3. Inside Searle's apparatus. 4. The step-by-step procedure. 5. Calculations and crucial precautions. And 6. Acing your Viva exam. Section 1. Why materials don't break. The secret strength of solids. Just take a look at the sheer variety of material stiffness on this table. Everything from spongy bone to high-strength concrete and titanium has a very specific stiffness threshold. We call this the modulus of elasticity, or Young's modulus. It's essentially an intrinsic property that tells us exactly how much a solid deforms under force. Section 2. Hooke's law and elasticity, the fundamental physics at play. So this brings us to the golden rule of this whole experiment, Hooke's law. Basically, as long as we're within the elastic limit, strain is directly proportional to applied stress. Think of stress as the force applied per unit area, so how hard we pull. Strain is the proportional deformation, how much it actually stretches. But crucially, you have to stay within the elastic limit. If you pull too hard, the wire suffers permanent deformation. Right, so here is our master equation for Young's modulus, which we denote with a capital Y. It's simply stress divided by strain. For our wire, Y equals m times g times L, all divided by pi times r squared times delta L. Now mass, gravity, original length, and radius are standard enough, but that tiny extension, that delta L, that is the ultimate prize we're trying to measure here. Section 3. Inside Searle's apparatus. The tools of the trade. Okay, let's look at Searle's apparatus. It's essentially two middle frames hinged so they can move vertically. There's a rigid crossbar holding a spirit level that rests on a micrometer screw. Now, when our wire stretches, one frame drops and the little bubble in the spirit level shifts. By turning the screw to recenter that bubble, we find our exact extension, our delta L. Now, you might be wondering why we use two wires, a reference wire and an experimental wire. Pay attention, because this is a massive Viva trap. We use two identical wires to completely cancel out external errors. If the room gets hot and the temperature changes, both wires expand equally. If the support happens to sag under the heavy weights, well, both drop equally. Those environmental errors literally just cancel each other out. Section 4. The step-by-step procedure. Executing the investigation. Let's act like lab detectives for a second and distill this down. First up, you suspend a dead weight on both wires just to make them nice and taut. Second, you measure the experimental wire's initial length and radius. Third, add your loads in half-kilogram steps. And finally, wait a minute for the wire to fully stretch, recenter your spirit level, and note the reading. Then you just repeat the whole thing for unloading. Section 5. Calculations and crucial precautions, the forensic math and common traps. When it comes to your measurements, you absolutely can't just measure the thickness once and call it a day. You have to measure the diameter at 5 different places and in 2 perpendicular directions. Why? Well, because nothing in the lab is ever perfectly manufactured. Wires actually tend to have a slight oval shape to them, so averaging these measurements ensures we get a highly accurate mean radius. And you really need to be precise here because of what I call the radius trap. If you look at our formula, the radius r is squared. Because of how error propagation works, any tiny percentage error in measuring that radius gets heavily multiplied in your final calculation. Honestly, a slight slip with your screw gauge here will completely ruin your results. To protect your data, you'll want to memorize this quick checklist. Move the micrometer screw in one direction only to avoid backlash error. Whatever you do, do not exceed the elastic limit. Make sure you keep your wires perfectly straight and free of kinks, and always apply your loads gently, without any sudden jerks. Section 6. Acing your Viva exam. Final insider secrets. Okay, picture this. Your examiner asks you, if I give you a much thicker and longer steel wire, how does its Young's modulus change? The answer is it doesn't. Not at all. Young's modulus is an intrinsic property of the material itself. A tiny short steel wire and a massive steel suspension cable have the exact same modulus. Let's leave you with this thought. If you add way too much weight and the wire doesn't return to its original length, you've crossed the line into permanent plastic deformation. But think about what that actually means for a second. What interatomic bonds were just forcibly rearranged inside that metal, all because you added one too many weights? It's pretty wild to think about. Good luck in the lab.